AdvSim, generating safety-critical scenarios for self-driving vehicles. As self-driving systems become better, simulating scenarios where the autonomy stack is likely to fail becomes important. However, identifying these scenarios is challenging, as there are exponentially many of them. Traditional approaches create safety-critical scenarios by hand, which is not scalable and might miss some cases. Most previous scenario generation methods work only for a handful of scene configurations, and are only adversarial with respect to a planning module that takes the ground truth actor states as input. In this work, we propose AdvSim, which modifies existing traffic scenarios in a physically plausible manner and creates new scenarios that cause full autonomy system failures. AdvSim is a black box adversarial attack that can be applied to any autonomy system. Given an existing scenario and its original sensor data, we first perturb the actor's behaviors in a physically plausible manner. Then, since the actor locations have now changed compared to the original data, we update accordingly how the SDV would observe the LIDAR sensor data based on the new scene configuration. Finally, we evaluate the full autonomy system on the modified scenario, compute an adversarial objective, and update the proposed perturbation using a black box search algorithm. Here we present an example of how we conduct realistic LIDAR simulation given a scenario perturbation of the actor's motions. In this example, we perturb all actors to the left by 5 meters. We update the LIDAR occlusion shadows and simulate the observed areas accordingly. Here's a side-by-side comparison of the 1-second LIDAR input sequence with and without the perturbation shown in red. The generated scenes are realistic and match the desired perturbation in actors' motions. Using this approach, we can evaluate the autonomy system on this new scenario and search for failure cases. We now show AdvSim generated scenarios for the P3 autonomy system and analyze the identified autonomy failure cases. We focus on an open loop scenario evaluation setting in which the evaluated autonomy system takes the past 1 second of LIDAR data as input and outputs a 5-second trajectory plan. We then unroll the plan and the other actors' trajectories for 5 seconds and evaluate the autonomy system's performance during that time horizon. The SDV is in blue and its past trajectory is plotted in blue with black waypoints, while the perturbed actor is highlighted in red. We first show the original scenario and then the AdvSim generated scenario. This scenario has a stationary bus in front and a crossing pedestrian. In the 5-second trajectory output from the P3 system, the SDV only moves forward a little. AdvSim perturbs the initial state of the bus in red by moving it into the left lane. Now, the P3 autonomy system does not detect the pedestrian, and the SDV's 5-second plan collides with it. To understand why the SDV behaves as it does, we now show the forecasted occupancy visualizations of the P3 autonomy system. The occupancy for pedestrians is shown in light green. As we can see, the pedestrian is perceived as part of the bus occupancy area, and hence the system misses the pedestrian detection. Here's another example. Originally, the blue SDV lane changes smoothly to avoid the stationary bus in front. AdvSim perturbs the bus to instead be reversing and blocking the road. Now, when the SDV attempts a lane change, it is rear-ended by another vehicle from behind. From the occupancy visualization, we can see the predicted bus occupancy blocks the whole lane. This causes the SDV to predict a dangerous large turn without accounting for traffic from behind. In this example, the SDV decides to safely overtake a slower vehicle in front by lane changing to the right lane, which is currently unoccupied. However, when we perturb a vehicle from behind to lane change into the right lane, the autonomy system instead outputs a plan that stays within the original lane and moves slightly to the left to avoid conflict with the perturbed actor. This causes a front-end collision. From the occupancy visualization in the planning horizon, P3 predicts occupancy on the immediate right side of the SDV, so the SDV steers left to avoid potential conflicts. We can also use AdvSim generated scenarios not only for testing, but also for improving the autonomy system via robust training. In this AdvSim scenario, the standard P3 system lane changes and is rear-ended from behind. After robust training with the AdvSim, the P3 system now outputs a plan that bypasses the bus smoothly and returns to its original lane quickly, without colliding from the actor with the actor from behind. Please see our paper and supplementary PDF for additional details and results. Thank you for watching.